Hello, in this video we're going to talk about closed subsets of R. So first, what is a closed subset of R, and then we will talk about one example of one example of a subset that is closed and one example of a subset that is not closed. So a subset is called closed if and only if the limit of every convergence sequence in S belongs to S. So in other words, if you take a sequence inside S that has a limit, if you take a sequence AN inside S that has a limit A, then whenever A is in S, then AN is in S, then the limit is also in S. Okay, so for the first example, we need a theorem, and this is a very useful theorem to keep in mind. If you have a sequence that approaches a number, then the sequence remains. So let me write down a diagram for this. I have a number b and I have a sequence an that an is always greater than or equal to b. If the sequence is always greater than or equal to b, then its limit is also greater than or equal to b. Keep in mind that in order to be able to use this theorem, we need the sequence to converge. Okay, so we will prove this theorem. Okay, so we're going to assume that an converges to a, and we want to show that, and an is greater than or equal to b, and we want to show that a is greater than or equal to b. So the way we want to prove this one is, I'm going to again look at the diagram on the right, and we are going to see why that should be true. So we want to show that the limit converges, the limit, which is a, is also going to be above b. Let's see what happens if a is not above b. So if a is not above b, a is on this side, then what happens is that an cannot get close to a. So it cannot get closer than this much to a. In other words, if I take my epsilon to be this distance from b to a, then I would violate the definition of limit. Okay, so what I'm going to be doing is I'm going to apply employ proof by contradiction. So on the contrary, assume a, which is the limit, is less than b. Let epsilon be b minus a in the definition of limit. So we have some integer, positive integer n, such that for every natural number n, if n is greater than or equal to n, then a n minus a is less than b minus a. That's the epsilon that I chose. So this tells us a n minus a is less than b minus a and greater than a minus b. Looking at the inequality on the right, we get an is less than b. But this is a contradiction because we know all of the terms of the sequence are at least b. That contradicts the assumption. Okay, so this proves the first part of this theorem. The second part tells us that if an is less than or equal to b, then the limit is less than or equal to b. So how do we prove for the second part? So now assume, how do we prove the second part? Now assume that an is less than or equal to b. So if an is less than or equal to b, then this tells us that minus an is greater than or equal to minus b, just by simply multiplying both sides by a negative sign. Now, limit of negative an is negative limit of an as n approaches infinity, which is just negative a. So therefore, by what we already proved, negative a is greater than or equal to negative b, and that implies a is less than or equal to b, and this completes the proof. Keep in mind that if the inequality is strict, then when you're taking the limit might not give you also a strict inequality. In other words, if you take something like this, 1 over n, this is a sequence that is positive, but limit of that sequence is equal to 0. In other words, that is not greater than 0. So keep that in mind. So when you're taking the limit from an inequality, the inequality is not going to remain strict. So that's one thing. The other thing you want to keep in mind is that you cannot just simply take the limit unless you know the limit exists. So you have to always make sure that you know the limit exists, and then you can say, well, if an is greater than or equal to b, then limit of an is greater than or equal to b. Okay, so now a couple of examples of sets that are, one is closed and one is not closed. Every interval of the form a comma b closed a comma b is a closed subset of R. Okay, so we will prove this one. Going back to the definition, we call a set closed if whenever a sequence inside the set converges to something, then the limit point is also in the set. So we're going to assume, suppose Sn is in the set and that converges to S. So Sn is less than or equal to b and greater than or equal to a. By the previous theorem, by theorem 2.7, the one that we just proved, the limit must be less than or equal to b and greater than or equal to a. So the limit must be in that range, and that means the limit is inside AB. And that's exactly what it means for the set AB, the closed interval AB, to be closed. Therefore, AB is a closed subset of R. So that's an example, I guess the simplest example of a closed subset of R. And finally, an example of something that is not closed, and that is Q. Q is not a closed subset of R. In order to show it is not a closed subset, what we need to do is we need to come up with an example of a sequence in Q whose limit is not in Q. Because again, think about what closed means. Closed means every sequence that is in S that converges, its limit is also in S. So we need to create a sequence in S, or we need to at least show that there is a sequence in S that converges, but the limit is not in S. How do we do that? We do that by simply using the fact that Q is sequentially dense. So since Q is sequentially dense, and this is something we discussed last time, there is a sequence Rn in Q such that Rn converges to root 2. However, root 2 is not in Q, and this implies that Q is not closed, because for it to be closed, the limit of every sequence in Q must be inside Q, and in this case it is not. Okay, so this is the end of this video, and feel free to follow along if you are interested in continuing with this subject. I will see you in the next video.